Welcome to our next video in the series on condensed matter theory. In this video I want to talk about why and how we can estimate the amount of admixture that you have when you talk about S-band, for example, between the 1s and the 2s orbitals when we construct our Wannier functions. And actually there is a very cheap way to see why you need the admixture of higher orbitals and to estimate how big that admixture is. And for this we can use the divergences in the potential and the inclusion of kinks and nodes this has this results to for the wave function. So your wave function must have kinks and nodes because your potential is divergent at some places. And we've already used this where we said, well, we have a divergent potential at the nucleus where we have our Coulomb potential. So our potential has the form of something like the electronic charge divided by the position of the atom, or the distance of your electron to the position of the atom. And we've already saw that such kind of potentials for a basis of plane waves leads to divergent interactions between them, and therefore it was nicer to go to a basis set of atomic wave functions. So let's investigate a bit more what such a divergence means for the wave function, and then use this to set conditions that our wave function must fulfill, which we then can use to make estimates on how a nice or good basis set should look like. So we know from the Schrödinger equation that the second derivative of your wave function is equal to the potential minus the energy times the wave function. And as your energy and potential are finite, that means your wave function has to be continuous and its derivative has to be continuous. And it's the continuous of the derivative that we will use. We can, instead of looking at a divergent potential at some point, look at the divergence at the point 0. You can always choose your coordinate system like this. And then we will use spherical coordinates. So in spherical coordinates we have a derivative with respect to the angular coordinates theta and phi, but we can also look at a derivative with respect to the radial coordinate, and that has to be continuous. Now if we look at our spherical coordinates, then we have r, the angle theta and phi, and r goes through from 0 to infinite. So at the point 0, in order to this to be continuous, we can look at the angle where you move in the other direction. So this derivative has to be equal to minus the derivative with respect to r of phi at r pi minus theta pi plus phi. So either going in this direction or moving in the opposite direction, where you have to map to each other, and if you have a derivative here that is positive and you move in the other direction, then it has to be negative. Well, this has to be true for any value of theta and phi. If that is true for any theta or phi, then definitely the sum for theta and phi minus theta pi plus phi has to be 0 of the derivative, or if you integrate over all angles 0 to 2 pi for the integral over phi, 0 to pi for the integral over theta, the derivative of your wave function with respect to r integrated sine theta d theta d phi evaluated at the point r is 0 has to be 0. So this is a necessary condition for your wave function to be continuous, and when it is violated, your wave function will be discontinuous. or we have a limit of R0 going to 0, 0 to 2 pi, 0 to pi of the gradient of your wave function dot with the radial vector sine theta d theta d phi evaluated at the radius r0 has to be equal to 0. And the reason to write it like this is that we now can use Gauss' theorem, because here we have an integral over the surface of a volume, which the volume we choose to be spherical, and we now can relate this to the integral over the volume of the sphere. So we use Gauss' theorem. That says that the integral over a volume of the gradient of a vector function is equal to the integral over its surface of that vector function times the norm at the surface times the integral of the surface. And when we do this, we already here have the gradient of the function. We'll get the second derivative, and then we can use Schrödinger's equation to relate this to the potential and the energy, which then gives you a relation between the derivative of the wave function and the potential. And then we can show that when that potential is continuous, this becomes 0. When that potential diverges, you get a kink. So we find then relations for the kinks, which we then can use as conditions we set on the basis functions that we are going to use. So let's do this for the specific case where we have a sphere around the potential at 0. So we have the limit of R0 going to 0, the double integral from 0 to 2 pi, 0 to pi of the gradient of the wave function dot r sine theta d theta d phi evaluated at R0 is equal to, we still have that limit of the radius of our sphere to 0. Now when we take a surface integral, we have to realize that the surface element r squared should enter. So let's put that on the other side. 0 to 2 pi, 0 to pi, 0 to R0, because now I'm going to do a volume integral, work in the other direction, grad dot grad, psi of r, sine theta, r square, dr, d theta, d phi. Now we can use the Schrödinger equation. We know minus h bar square 2m phi of r is equal to or plus the potential times psi of r is equal to the energy times the wave function. If we now insert this, then we find that this is equal to the limit r0 to 0, 1 over r0 square, the triple integral to m over h bar squared, the potential minus the energy times the wave function, and then sine theta r square dr d theta d phi. And this is equal to the integral that we had before, the integral over the derivative of the radial part of our wave function evaluated in the origin. Now, in order to evaluate this integral where we have the potential, we can make a Laurent series of the potential. VR minus the energy is, well, it's Z divided by R plus, and the rest is an analytical function. So that is just going to be a Taylor series, C1 dot R plus higher order terms. So coming back, this is the limit of R0 to 0, 1 over R0 squared, and then our triple integral, 0 to 2 pi, 0 to pi, 0 to R0 to m over h bar squared, z over r, phi of r, sine theta r square dr d theta d phi. Well, we have here an 1 over r times r square, which is r, so its integral is an r square. Here we have a c0 times r square, and its integral will be an r cubed. So we have limit r0 to 0, 1 over r0 squared, 2m over h bar squared, 4 pi z r0 squared over 2 for the z over r times r squared, plus 4 pi z0 r0 cubed divided by 3, plus something r0 to the fourth, etc., etc. Phi. And now here, in principle, we have to integrate our wave function over the volume, so you get a volume average, but we take r0 to 0. So this is just the value of the wave function at 0. Well, 1 over r0 squared times r0 squared is 1. 1 over r0 squared times r0 cubed is r0, and then we take the limit to 0, so they all disappear, so all our higher orders are not important, and what is left is 1 over 4 or 4 pi mz divided by h bar squared. Now please have a look that here we didn't put in our 1 over 4 pi epsilon 0 e squared, so there you have to be a bit careful about the units. That's how we just expressed our potential. Everything is absorbed in z. So we find that the derivative at the origin is either 0 when the potential is non-divergent, so your wave function is continuous, or when we have a Coulomb potential with 1 over r divergence, then there is a kink in the wave function. Also note that if our wave function lives on spherical coordinates, then we can write this as spherical harmonics times a radial wave function. And the integral over a spherical harmonic is 0 unless the wave function has 0 angular momentum. So we find that for a single atom with a single Coulomb potential, the P, D or F wave functions, all with finite angular momenta, are 0 at the nucleus, which is fine. You have a diverging potential times a wave function that is 0, so everything is continuous. But the S wave functions with 0 angular momentum locally, there the wave function is non-zero at the nucleus, and you have a kink in that wave function. Now we can use this to make constraints on how our wave function has to look like. So if you take a single atomic wave function, then you know that the s orbital has a kink and is finite, whereas a p orbital would have a kink when you go through the nucleus. And is 0 at the nucleus. Now, that's for a single atom. What happens when I have not a single atom, but a lattice? with a distance a between my atomic sites. Then for the site where our atomic wave function is centered, all is fine. You either have an S wave function with a kink or a wave function with higher angular momenta where the wave function itself is zero and therefore the size of the kink is zero and everything is continuous. This is of course no longer true when we look at the nearest neighbor. There your S wave function is continuous and continuously going through a point in space where the potential diverges. And we know in order to fulfill Gauss' theorem you either have to be zero and be continuous or you have to have a kink. So this wave function has a problem with the divergent potential at the nearest neighbor. Now what we drew here is the 1s atomic orbital. We can also look at the 2s atomic orbital. We should have made the sketch a bit better here, that this is not so large. Now, in order to make sure that our basis function fulfills Gauss' theorem, and it is important to fulfill Gauss' theorem because we're talking about infinities and infinite divergences. So that's the first thing that you have to fulfill. In order to fulfill Gauss' theorem, this wave function either has to be zero or has to have a kink. When it has a kink, then we should add nearest neighbor s orbitals. But it's nicer to stay localized on this site, and we can do this by adding a nearest neighbor 2s orbital. The 2s orbital is of different sign here. If you start with the same sign, and is much larger because it lives further outside. So by adding a little bit of 2s, I can make sure that my wave function is zero there. So my 1s local Warnier function is going to be a linear combination of the atomic 1s wave function plus the atomic 2s wave function, such that the Warnier function at the nearest neighbor atomic distance is equal to zero. And of course, for the next nearest neighbor, you can also start to add the 3s to make things zero again. But your wave functions exponentially decay, so those prefactors pretty quickly will go to zero to make everything nice and convergent. So a very cheap way to find out what your Warnier functions roughly should be is to start with the atomic basis functions, look at their value at the nearest neighbor, then add the next higher principal quantum number to them to make sure that they are zero and that state. And that will give you reasonable solutions to the states that you have. You make a Fourier transform of those and you get your band states that you have. And actually this works reasonably well. It's not perfectly accurate, but it's not too bad either. Especially under ambient pressure, where you try to optimize where you're free to optimize the atomic distances to minimize both the atomic energies as well as the kinetic energies in your system. So thank you very much. That's what I wanted to tell about divergent potentials and the results in kinks and nodes that follow from this, and how we can construct in a very simple way wave functions in a solid. Stay healthy. We'll see each other in the next video.